are usually used to send or receive the data between the process, and also the IPCs are used to synchronize between the process. So as we know that each process has its own virtual memory, and the process cannot access the virtual memory of other process. Hence, there is a need for inter-process communications. And IPCs are usually, there are two types. They are communication based or synchronization based. So we have communication based IPC and synchronization based IPC. Communication based IPCs are used to transfer the data, whereas the synchronization based IPCs are used to synchronize between the process. So a communication based IPC, we have data transfer based and memory sharing based. So in case of data transfer based IPC, the data is transferred from one process to the other process using specialized data structures such as the pipes, FIFO, message queue and sockets. Whereas in memory sharing based, there is a common memory that is shared between the process, and the process can exchange data by writing to the common memory that is also called as the shared memory. And we have the synchronization based IPC, in which these are used only to synchronize between the process, and they are semaphores, mutex and condition variables. So mutex and condition variables are used to synchronize between the threads. We will see each of this in depth in upcoming video sessions. Hello and welcome. In this video session, we will see the concepts and programming of pipe and FIFO. Pipe and FIFO are used for communicating between the process. IPC is nothing but inter-process communication. A pipe is actually a byte stream based communication used between the process. A pipe has two ends. The one is a read end and the other is a write end. Let's see the pipes with this example. So in this figure, we can see that this we can imagine like a pipe, and this pipe has two ends, the end here and one more end will be here. So this can be considered as the right end and this can be considered as the read end. We will see in details what is the descriptors here. So we have a process on one side and the other process on other side. The process can, these two processes can communicate, or this process can send data to this process via pipe. The pipes are considered to be unidirectional data flow. This means the process on left hand side writes to the data on the pipe, and the data is read on the pipe that is present here. With an example, we will be able to understand more on the pipes. So let's see what are the features of the pipe. A pipe is an unidirectional. As shown here, when a data is written here, it only flows in one direction and the data is being read out from the other end. And a pipe, it has a limited capacity, like usually 64 kilobytes is the pipe capacity, and a pipe is nothing but, this pipe is nothing but a buffer. It is maintained in the kernel memory. So this, what we see here, the pipe is nothing but a buffer, and it's like a data structure or buffer that is present in the kernel memory, and this has a, usually the size is 64K. And when the pipe is full with the data, the new data cannot be written on the right end. Now let's consider that this pipe has the maximum number of data. Now the pipe, the process that is writing on the right end cannot write until the reading process has read the data. So whenever the pipe is full, any new writes to the pipe will block the write process. Also, the writing to the pipe puts the data to the pipe, whereas reading the data removes the data from the pipe. So in this case, we can consider a pipe like a normal pipe what we have in which there is a flow of water. So we can consider that when water is poured here, the water comes out from here. When the tap is on, the water can flow out from the pipe. So the same analogous can be used here also. So let's say the tap is closed here, and if the pipe is full of water, the new water cannot enter into the pipe. And similarly, as soon as the tap is open, the water can flow and the new water can enter inside. Similarly, the data that is present in the pipe can be read by the reading process, and the once the data is full in the pipe, the write to the pipe will be blocked. Now let's see the creation of the pipe. So in order to use the pipe, we need to include UNI std.h, and here, as we know, we have discussed that pipe has two ends. One is the writing end and the other is the reading end. So we need two file descriptors. So pipes are operated on the file descriptors. So in this case, we consider an array of two integers, and we call a function called as pipe and pass the file descriptor, and in turn the file descriptor will be filled with the read end and the write end. So a pipe, it returns two file descriptors. One will be present in fd of 0, as fd is an array of two integers, fd of 0 and fd of 1. So we can say that fd of 1 is the write end and fd of 0 is considered as the read end. So in this case, when we open a pipe, we get fd of 0 and fd of 1. So fd of 1 is considered to be the write end and fd of 0 is considered to be the reading end of the pipe. Also, the data flow direction is unidirectional. That is, from the data flows from the write end to the read end. And if the pipe function is successful, it returns a 0, or if there is an error, it returns a -1. So now let's consider the application where the pipes are used. Pipes are generally used when we have to communicate between the related processes. For example, when we have a parent and a child process, child can send the data to the parent, or parent can send data to the child via pipes. Also, as a very important note, when a parent creates a child process after forking, the child process inherits the copies of its parent's file descriptors. So all the pipe file descriptors will be inherited from the parent process to the child process. We will see this with an example for more accurate understanding. Now let's consider a situation where the parent process creates a child process, and so if a parent process has created a pipe already and then it forks a child process, then the figure on the left hand side can be considered. In this case, the file descriptor, that is fd of 1 and fd of 0, will be shared by both the parent process as well as the child process. So this will be the situation when a parent process already has opened a pipe and then forked a child process. So now, for more application purpose, what we will do is, in the child process, we will close the reading end. And for example, in one of the process, let's say the parent process, we will be closing the reading end, and if the data has to be passed from the parent to the child, and then the writing end in the child will be closed. So when we close, we can see a similar scenario that is present on the right hand side. So let's say the parent process has to send some data to the child process, then this will be the left hand side will be the initial situation in which both the file descriptors are available to both the process, that is the parent process and the child process. But after the forking of child process, one process will close the unused file descriptor of the pipe. So in this case, if we have to pass the data from parent to child, then the parent will be closing its read end and child will be closing its write end. Similarly, if child has to send the data to the parent, then the child will close its read end and the parent will read from this while the parent will close its write end. We can see this with an example in the program. Also, while dealing with the pipes, we have a signal called as sick pipe. A sick pipe is a signal that is usually occurs when there is a broken pipe. This means this signal is sent to the right end process when the read end is closed. Now consider a pipe, and when two processes are communicating between each other using pipes. Now when the sender process is writing to the right end and the receiving process is reading the data from the read end. But now as soon as the read end the process which is reading, if it closes the file descriptor, then a signal is sent to the process which is writing to the pipe. We will see the SIG pipe concept as well in the example. Now let's go to the example for better understanding. Now we have a simple program here. In this, we are including the required header file. Now, as discussed, we will be declaring an integer array. Let's consider that it has a FD of 2, and we have taken some buffers for pipe operation. Now let's open a pipe. In order to open a pipe, we have to call the function pipe and pass the file descriptor to the function. And if it returns -1, that means the pipe is not created and we have an error and we exit from the program. If the pipe is successful, -1 is not returned and it enters to this line. So now we have FD of 0 and FD of 1. As mentioned in the presentation, FD of 1 is the write end and FD of 0 is the reading end. So now if we come back to the program here, FD of 1 holds the writing end, FD of 1 is the file descriptor of the writing end, and FD of 0 is the file descriptor of the reading end. Now we can write to the right end of the pipe. This is similar to the file operation what we have discussed in the earlier video sessions. Like we are going to use the write system call, and the buff in the buff we are storing this string that is nothing but the pipe data flow demo. Some string we are storing in the buffer, and now this buffer we are writing via the file descriptor FD of 1. So the whatever is the length of the buffer will be written to the pipe on the right end. Now in order to read the contents of the data from the pipe, we have to use the system call read, and we have to specify FD of 0. So FD of 0 is the file descriptor for the reading end of the pipe, and the read data is being stored in the new buffer called as data. And if you note here, we are reading only 5 bytes of data. So this read and write operations are similar to the file operations that we have discussed earlier. We can specify the number of bytes that we can read from the pipe. So now in the first read we are reading 5 bytes, in the second read we are reading the next 5 bytes, and in the next read we are reading the 10 bytes of data from the pipe. Now let's compile this. Now let's run the program. If you see here, the program has written the complete strings onto the pipe that is on the right end of the pipe, and now the read system call has read the first 5 bytes. So the first 5 bytes, pipe and the space, we have read the first 5 bytes. Then the next 5 bytes, that is the data and the space, that is read here, and then we have read 10 bytes of data. So now we have read the 10 bytes of data. So in this case, this read operation is similar to the file operation what we have discussed. That means, let's say if the number of bytes in the pipe is less than the number specified here, then we will be returning the number of the bytes actual read. In this case, we have not shown the actual bytes read, but this function call is similar to the read and write that we have discussed earlier for file operations. So by this we can say that we have created a pipe here, and while creating a pipe we have passed the file descriptor that can hold an write end and a read end file descriptor, and in this case of demo we have a same process, writing to the write end and reading from the read end. So in this program there is only one process running, and this program is just to show how the basic operations on pipe can be done. So in the next program, let's use pipes on two different processes, that is between the parent and the child process. Okay, so in this program we are including the required header files, and if we see here, if we recollect that in the previous video sessions we had done how to create a child process from a parent process. So in this case, before creating a fork, the process has created a pipe. So let's go back to the diagram what we had discussed here. So this is the situation. So on the left hand side, what we are doing is we are first creating a pipe. So first we are creating a pipe, and then we are forking a child process. So once the child process is forked, the child process and the parent process shares the file descriptor of the pipe. So fd of 1 in both the process represents the right end of the pipe, and fd of 0 in both the process represents the read end of the pipe. Now in case -1, that means the fork had a problem and it did not create it was not successful. Case 0 is when it has a child process and the default will be a parent process. So this is a parent process, so this will be the child process. So you can go back to the previous parent and child process explanation in order to understand the parent and child process creation using fork. Now in this child process we are closing the right end. So we are trying to achieve the one which is in the right hand side of the figure. So in the child process we are closing the right end. So this fd of 1 we are trying to close, as we are not intended to write to the pipe in the child process. And after closing, Now in a while one loop, so for colon is similar to a while one loop. In a forever loop, we are reading the bytes from zeroth descriptor, file descriptor. So the child process reads from the zeroth array index, that is nothing but the read end of the file, and the read will give the number of the bytes that is read. And similarly, if it has read -1, then we exit. That means there is a problem in reading. And if the number of bytes that is read is equal to 0, that means the other end of the pipe was closed. So if the parent process closes the right end of the pipe, then the number of the bytes that will be read in the child process will be 0. So as soon as the parent process closes the right end of the pipe, we break from the loop, and the child process, we close the file descriptor of the read end and exit the child process. Now coming to the parent process also does similar to the child process, but the parent process will hold only the right end and it will close the read end. So here the parent process is closing the read end, and now the parent process is writing the data that is passed from the command line argument, and it writes to the right end of the pipe. And after a sleep of 2 seconds, it closes the right end of the pipe. So as soon as the right end of the pipe is closed, in the child process, the number of the bytes read from the pipe will be 0. Let's compile this program to understand better. Now let's run the program. We have to pass the command line argument. Now in this case, we are running the program with the command line argument. Now the parent process is writing the command line that we have passed onto the pipe, and the child process is reading the read end of the pipe. Now we can see that what the parent process has written to the right end of the pipe is being read from the child process from the read end of the pipe. So now as soon as the parent process, after writing to the pipe, it closes the right end. So now after a sleep of 2 seconds, the parent process is closing the right end. So as soon as the parent process closes the right end, now when the child process tries to read the contents of the pipe, it encounters number of the byte read equal to 0, and it prints this line. That is nothing but it says that the parent has closed the right end. This is the print we have got. So as a note here, whenever let's go back to this figure. So whenever any process has opened a right end, and when the other process has opened the read end, the data flows from the right end to the read end. Now if the right end process which has opened the right end has closed the file descriptor, then when the process in the read end does a read, then it returns the number of the byte read as 0. Now let's see the SIG pipe program. This is a program to demonstrate the SIG pipe. This program is same to the previous program what we have discussed, but only difference is in this case the In this case, the read end will be closed, and as soon as the read end is closed, the right end, the process running in the right end will receive a sig pipe. So let's see this program. So in the same way, we have a fork. We have created a fork, and we have a pipe here. We have created a pipe before, and then called a fork. And case 0 represents the child process, and default represents the parent process. Now the child process closes the right end, and same way the parent process closes the read end. Now the child process runs in a while one loop or forever loop, and now it reads the contents from the pipe from the read end. And now if we see here, at some point the read end closes. The process running in the child closes the read end. So as soon as the read end is closed, the process running in the right end receives an sig pipe. So by default, the default action of sig pipe is to exit the parent process. Not exactly the parent process, it exits the process in which the signal is received. So in this case, a sig pipe is received to the parent process, and the parent process will be terminated. Let's compile this to understand. So let's run the program. Let's pass some parameter. If you see here, the parent has passed hello onto the pipe, and the child process has read it. But after that, the child process has read the close end. That means after reading the data from the pipe, the child process has performed a close of the read end. So now let's come back to this. So now the child that was receiving the data has closed the read end. So if the read end is closed, a signal will be sent. The signal is called a sig pipe, will be sent to the process which holds the right end. So now the sig pipe will be received in the parent process, and the parent process will be terminated. So we can see that here we can see this print here, about to write data to the pipe. If we come here, we can see this about to write the data to the pipe, but after that the parent process has terminated. So what we can conclude is, a sig pipe, when it is received by the process will be terminated, and sig pipe is received if the process running on the read end closes its read file descriptor. Hello and welcome. In this video session, we will discuss on the concepts of FIFO. FIFO is nothing but first in, first out. FIFO is also similar to a pipe. In the previous video session, we saw the discussion on pipe. Pipe is also in fact first in, first out. Let's see what are the difference between a FIFO and a pipe. A FIFO is also called as a named pipe. And the main difference between pipe and FIFO is that a FIFO in fact has a name in the file system, and it is opened in the same way as we open a regular file, whereas a pipe does not have any name in the file system. This means that the FIFO has a persistent in the file system, and even after the program stops running or it exits, the FIFO still remains in the file system as if it is a file. But a pipe will be deleted, or a pipe will not exist as soon as the process which has created it terminates. Also, one of the main difference between a FIFO and a pipe is a FIFO can be used to send data between two unrelated process, but a pipe was used only for communication between a related process like a parent and a child. A FIFO, once it is opened, we can make use of all the system calls that we use on a files like open, read, write, close. So in order to operate on the FIFO, we make use of the same system calls that we make use on the normal or a regular file. A FIFO also has a write end and a read end similar to a pipe. Write end is one in which the data is written onto the FIFO, and read end is the one in which the data is being read from the FIFO. So a FIFO is nothing but a first in, first out. The first written data will be read out first. Let's see the syntax of creating a FIFO. In order to create a FIFO, we need to include sys/stat.h, and make FIFO is the system call used to create a FIFO, and it takes two arguments, the path along with the name as well as the mode. We will see in details how to use make FIFO in the example. Upon success, it returns a 0 or -1 on error. Now let's see some examples in order to understand the FIFO, working of a FIFO. Now let's open a simple program. So here we need to include all the required header files, and here we have a main function and we are creating a FIFO. So before creating a FIFO, we have to specify the path in the file system where it is created. So here we have chosen /temp, and the name of the FIFO will be my FIFO, and this is a buffer used for reading and writing the data onto the FIFO. Now make FIFO is the system call to create a FIFO, and the first argument is the FIFO path where we are about to create the FIFO. And so here we are specifying /temp/myFIFO, and this is the mode in which we are going to create a FIFO. So if we see this is similar to the file creation, in which we are creating a file and we are specifying the permission in which we have to create the file. In the same way, a FIFO will take the path name in which location it needs to be created, along with the name of the FIFO and in which permissions it needs to be created. Now, once it is created, we have to open the FIFO in order to operate on the FIFO. Now, we are opening this my FIFO that we have created, and in this case, we are opening in the write only mode. So here if you see the permission what we are creating is 660, that means user can read write, group can read write, and others don't have any permission. And now we have opened the FIFO that we have created, and in a while one loop we are getting the string from the user input and using the write system call, and now FD refers to the FIFO, and we are writing the data onto the file descriptor that we have opened, and we are writing the data that is present in the ARR2, that is nothing but the buffer in which the string is stored. And finally we close the file. So now let's compile this program. Let's name this as a write. Before executing this, let's go to the location of this /temp. So here we are in /temp location, and let's see the contents of this. So in this, if you see, there is no myFIFO file which is present. So myFIFO is the FIFO which is going to be created. So if you see here, there is no FIFO by the name myFIFO. Now executing a write FIFO program, let's consider the read FIFO program. So in this program, we are including the required header files, and here we open the myFIFO. In the write FIFO program, we had specified the path of the myFIFO. So now we are specifying the same path. Now let's open the myFIFO in read-only mode. So this operation is similar to opening a regular file. So now, as we have mentioned in our presentation, that FIFO is also considered as the regular file operation. So all the system calls of regular file can be used on the FIFO. So now by opening, we are opening the myFIFO, and we are specifying the read-only mode, and in a while one loop, we can read the FIFO by specifying the file descriptor. So open returns the file descriptor. Now FD1 represents the FIFO which we have opened in reading mode, and by calling a system call called as read, we can read the contents of the FIFO onto the string 1, which is nothing but a buffer here, and the red string is printed onto the screen. And finally, we can close the file descriptor. Let's compile this program. Let's name the executable as read here. So now we have two executable files. One is the read, one is the write. So write is the executable file created by the write FIFO program, and read is the executable created by the read FIFO program. So now let's run the write FIFO program. Now in the other tab, let's run the read FIFO program. So now we are running two processes in parallel. That is, write process, write runs as a separate process, and the read program also runs as a separate process. So now we have two unrelated processes running in the memory. Now let's enter some parameter. So in the write program, we have entered hello1, and if you see here in the write program running, we have received the data from the FIFO. So from this process, we are writing to the FIFO that is present here /temp/myFIFO, and the read program is also reading from the same /temp/myFIFO, and the data that has been read is printed onto the user. So now we can see that we are able to send the data from one process to the other process, and both the process are not in a not related process. If you can see, we should have got this data that we have sent from the write program. onto the read program. So this is the data that we have received in the other process. Now let's see one more aspect of the FIFO. Now this is the path in which we have created the FIFO program. Let's open the write program as well. So in this case, we have the write FIFO program and the read FIFO program. So both the program are referring to the same FIFO, that is /temp/myFIFO. Let's go to /temp. This is the path where the FIFO is created. Now if we do ls-l, we can see that myFIFO is the FIFO that is created, and we can see that it is the type of the file is P here. So that this is nothing but the named pipe. Now let's remove this myFIFO and let's check the contents. So now myFIFO program is not there. Now as soon as we run this write program, we will be creating a myFIFO. For example, when I run the write program, so we are calling a mkFIFO. By calling mkFIFO, we are creating the FIFO for the first time in the permission given. Now let's run this program. Now the write program is run, and now if we check the contents of temp, we can see that we have created a myFIFO. This is nothing but a named pipe.